Hello and welcome again to Advanced Chemistry with Pastor Dan. We're looking at Graham's Law here today, Graham's Law. So in order to do this, we're going to talk a little bit about kinetic theory. Kinetic theory is defined as the explanation of movement of electrons. In order to do that, there are a few assumptions we have to make. Not all of them are correct. We have to just simply hand wave saying, yeah, we know that's not perfect, but that is what we're going to do, and we're going to use that to get us to Graham's Law. All right, so the first assumption we make is that gas is composed of many molecules in constant motion. They don't ever slow down, they're in constant motion. That's the first assumption we make. The second, volume of all gases is equal to the total volume. So I take each individual gas, if I add them up, it's the same as the total volume. That makes sense. Third one, we're going to start to get a little bit of there's no attraction or repulsion rate to molecules. Actually, we do have some, but we're just going to hand wave that for right now. We're going to eventually get to something called van der Waal, where we'll take care of those. Collisions between molecules are completely electric, so if it comes in at 100 meters per second, it bounces back at 100 meters per second. There's no loss of energy. Again, And then lastly, all molecules have the same energy, the same temperature, so we're assuming everything's the same in order to make that work. Now, what we do that then is we generate something called the speed of molecular movement. We use that for Graham's Law. Now, this is something called effusion. And the equation for effusion, E is equal to 1/2 m, that's the mass, u squared. Now, we're going to rearrange it because that E value doesn't help us a whole lot. So what we're going to do, E is the energy, okay, energy involved. M is the mass of the gas. R is what we call the root mean squared. It's the velocity of the molecule. And then R is...
The U is the root mean squared, sorry.
Gas law constant, not the same as the R in the ideal gas equation. It's 8.314 joules per mole Kelvin. And then MW is molecular weight. Rearranging this equation to solve for U then, because that's what we're going to look at. The basic speed of velocity of the root mean squared is 3RT over MW square root. That's our answer right there. All right, now let's do a problem. So we have determined the rate of effusion of sulfur trioxide gas at 35.20 degrees Celsius. Start with the equation. Now, 3 is 3. R is 8.314 joules per mole Kelvin. Temperature 35.20 plus 273, 308.2. Now we got to get that mass, 80. How did I get that? Sulfur trioxide, sulfur is 32. Oxygen 16 times 3 is 48. 48 plus 32, 80 grams per mole. We're going to take the square root of that. But we got to get rid of some units here. So there's 2 additional fractions we're going to add. We're going to say that 1 kilogram, meter squared per second squared, is a joule. And we're going to say 1,000 grams is a kilogram. That way my kilograms will cross out, my grams will cross out, my moles will cross out, moles, mole right there, mole, mole. My Kelvin will cross out, joules cross out. All we're left with is meter per second squared, like that. So if we take their numbers, 3 times 8.314 times 308.20 times 1,000 equal, divide by 80 equals square root. We get, where we at, 5 sig figs. We end up with 309.98 meters per second. Those things are moving. All right. Now I'm going to give you another one. I'm not going to show the work. I'm just going to give...
There are no sig figs for this problem, so just go with 4.
Answer. If you have a problem with it, send me an email. We'll talk about it, ltswpd@gmail.com. Remember to share, like, subscribe, all those kinds of good things. So that's the answer, 393.4 meters per second. Now we can also, talking about what we talked about last year, diffusion. Diffusion, process of moving from a region of high concentration to a low concentration. Alrighty, now, the way that we actually got those is using that U value. If we take the square root of 3RT MW, 1 over MW2, those get flipped, and that's how we got the Graham's Law equation we worked with last year. MW2 over MW1 is equal to D2 is equal to the rate involved that way. Don't remember those? Go back into Chem 1 under gas laws, Graham's Law. All right. Remember, if the rate is greater than 1, then it's faster. Less than 1, it's slower. Let's look at a problem. Now, we're going to do a little bit different, a little more complicated than last year. calculate the molecular mass of a gas that diffused at 0.555 times slower than chlorine. So what we're saying here is that the R some gas, we don't know what it is, over chlorine is 0.555.
Now that's
Now
all
that's
that
gonna
we're
be
going
it.
to work with. That's all we're going to work with. We're not going to worry about this equation or this number is this ratio.
Equal to 71 grams per mole over molecular weight. We don't know molecular weight, where MW is, so we're solving up for that. Now, 0.555, this value here is just that. Solving up, we're going to take the square both sides. When we do that, then we're going to swap partners. So we're going to get 71 grams per mole divided by 0.555 squared. 0.55 squared is 0.308. 3 sig figs, we get an answer of 231 grams per mole. That's the molecular weight. All right, molar mass, molecular weight. Okay, again, we're going to do 2 problems. Check those. Any questions, email me so I want to know the rate of effusion. And I want the density. Pause it, work through it. Any questions, let me know. Here we go. And first answer and the second answer. All right, that's it. No problem. Take care. God bless. Bye.